Dear students, now we'll see inductors in series and parallel. First we'll see inductors in series combination. So you have seen in current electricity chapter how to calculate the equivalent resistance of combination of resistors, whether in series and parallel. Similarly, we will derive the inductors connected in series and parallel instead of resistors. Here let we consider two inductors are connected in series. The two inductors connected in series, and L1, L2 are two self-inductances of the two coils. So here the EMF induced in two individual inductors is E1 and E2. So E1 is the induced EMF produced in first inductor, E2 is the induced EMF produced in second inductor. Here we need to calculate the equivalent self-inductance. Here two inductors I have taken. So if you replace these two inductors with a single inductor in such a way that that equivalent self-inductance, it should be equal to this total combination of L1 and L2. So here I will redraw this circuit. So replace these two inductors with a single inductor. That equivalent inductance of this inductor is LS. So this total induced EMF across this equivalent inductor, let it be E. So current it will be I. So we need to calculate this LS value. And we know that the total induced EMF in the circuit, it will be E. So we have taken the two inductors. So the total induced EMF, it will be divided across E1 and E2. So we can write the total induced EMF in the circuit, it will be equal to the sum of individual EMFs across these two inductors. At any instant, the rate of change of current through these inductors, that is a di by dt. So in series combination, here you should remember di by dt, the rate of change of current through each inductor, it will be constant. But EMFs induced across different inductors, it will be different. That's why the total EMF induced in total circuit, it will be equal to the sum of individual induced EMFs. So E is equal to E1 plus E2. We know that, let this equation 1, induced EMF formula minus L, for across L1 I have taken E1 is equal to minus L1 the di by dt. So this di by dt is a constant throughout the circuit, whether it is L1 and L2. Similarly, induced EMF E2 is equal to minus L2 di by dt. So and the total induced EMF is equal to minus, instead of L1 and L2, what we have taken? LS di by dt. Now this E1, E2, E, substitute in equation 1. From equation 1, instead of E, minus LS di by dt is equal to minus L1 di by dt plus, minus L2 di by dt. So here di by dt, it will take common, both are getting cancelled. So finally we can write this minus also getting cancelled. From this we can write LS is equal to L1 plus L2. So this is the expression for two inductors connected in series combination. Suppose if n number of inductors connected in series combination, let n number of inductors connected in series, then Ls is equal to L1 plus L2 plus and so on plus L. So this is the equivalent self-inductance of a circuit. Next, inductors in parallel combination. Here also I'll take the two inductors. Here the total current it is I. So the current it will be divided in two parts, that is I1 and I2. Let this self-inductance of this inductor is L1 and this one is L2. And these two are connected in parallel. So the major difference between series and parallel combination is, in series combination, what is the constant here? At any instant, the rate of change of current through each inductor, it will be same, but the induced EMFs, it will be different. But here, total current it is I it will be divided as I1 and I2, that based on the value of this L1 and L2. So here the total current it will be that is a different across different individual inductors. So here the rate of change of current at any instant it will be different across these individual inductors. But what is a constant? The induced EMF across each inductor it will be constant. So here E is constant. So remember this point, in parallel combination of inductors, the induced EMF across all the inductors it will be constant, but the rate of change of current it will be different in different inductors. So here we'll write E, it is a constant, and now that current it will be divided into two ways. One is I1 and I2. So that how to calculate the total sum of the current? I is equal to I1 plus I2. I is equal to I1 plus I2. Let this equation 1. So here L1 and L2 are two individual self-inductance of the coil. So for this one we can write equivalent circuit. It is a LP and the induced EMF it will be E. So now I will calculate individual currents, means di1 by dt in this one and di2 by dt in this one, because now we will calculate the individual rate of change of currents in L1 and L2. So across L1 I will write that induced EMF expression E is equal to minus L1 di1 by dt, and across L2 E is equal to minus L2 di2 by dt. Now the total means if for equivalent circuit E is equal to minus LP di by dt. So now from this we can write okay, first this equation 1, it is a differentiate with respect to time on both sides. Differentiate equation 1 with respect to time on both sides. So now we'll see di by dt is equal to di1 by dt plus di2 by dt. So from these three equations we can write directly di by dt. From this one di by dt we can write minus e by lp is equal to, from this one we can write di1 by dt is equal to e upon minus l1, so minus e by l1. So similarly from this one, so here also it will be minus e by L2. So here minus c getting cancelled. Then finally we got 1 by Lp is equal to 1 by L1 plus 1 by L2. So this is the expression for calculating equivalent self-inductance of the inductors in parallel combination. Suppose if n inductors are connected in parallel combination, so 1 by L1 plus 1 by L2 plus and so on plus 1 by Ln. So this is the expression for parallel combination and this is the expression for series combination.